My name is Peter Bartlett. I'm very happy to have you here for the second workshop of the Computational Complexity of Statistical Inference program, one of the two programs we have running this semester. The workshop is called Algorithmic Advances for Statistical Inference with Combinatorial Structure. First of all, a big thank you to the organizers, Laurent Massouli, Po-Ling Lo, and Jiaming Zhu. Thanks to them for organizing a great program this week. So I'll hand over to Jiaming in a second to introduce the workshop. Just a few comments about food and drinks. Please don't bring them into the auditorium. They're all provided outside there. We try to keep the auditorium clean. You need to wear masks inside. I guess you've all been told this. On the far side of the building, if you want to leave bags or things at lunchtime, you're welcome to do that. There are lockers over there with PIN numbers. And we're running today in a hybrid format. So also on Zoom with a Zoom audience. Our videographer here is Omid Farr, and he'll be assisting with connecting people throughout the day to the speakers throughout the day. And finally, a big thank you to Keilani Penlan, our events coordinator at the back, who did all of the local arrangements. Thanks.
Thanks, Peter. Hello, everyone. On behalf of the conference organizers, workshop organizers, Laurent Massouli, Po-Ling Lo, and myself, we would like to once again thank everybody who come to attend this workshop, both in person and virtually. So it's my great pleasure to speak here. In fact, Laurent, so he is the main organizer who is in charge of everything, so he should give the intro. But unfortunately, he couldn't be here due to the travel restrictions. Po-Ling also cannot be here, so they want me to pass their sincere regret for not being here to everybody. So also, if you have any complaints about workshop, please direct them to them, not to me. Just kidding. Okay, so I will also take this opportunity to thank the program organizers for giving us this wonderful opportunity to organize this amazing workshop. Also, big thanks to the Science Institute, especially the amazing staff teams who are actually the main persons behind the scene to set up the website and take care of all the logistics. Okay, speaking about logistics, just a quick few things. So we have a little bit unusual early start at 9 a.m. every day so that our European friends won't need to stay too late. Also, we try to leave like ample discussion time for you to discuss and network with other peoples. And also, like during the talk, please feel free to speak out if you have any questions. So for Zoom participants, you can just feel free to unmute yourself. For people in this room, please speak loudly. If needed, we can pass the microphone to you. Okay. Okay, so I think that's all I want to say. Let me just say a few more words about the workshop. So continuing from this bootcamp and the previous workshop, so we are continuing to explore the intersection between statistics and the computation. So the theme of this workshop will be on algorithmic advancements. So like we've learned that in many high-dimensional statistical inference problems, we actually encounter big gaps between the information theoretical limit and the computational limit. So therefore, on one hand, it'll be very interesting to design like efficient algorithms to succeed all the way down to the conjectured computational limit. On the other hand, to understand this computational gap is also interesting to characterize the performance limits of these different efficient algorithms. So toward this end, in this workshop, we have a wonderful list of speakers who will cover a variety of different algorithms and ideas, such as approximation parsing, gradient descent, spectral methods, iterative methods in general, in search of the optimal algorithms in a variety of different learning problems, such as like graph alignment, learning from mixture models, matrix or tensor estimation, graphic models, and etc. So without further ado, let's maybe move on to the first talk. Let's see. So the first talk actually will be presented by Amin Coja-Oghlan. So it's my great pleasure to introduce Amin, who is actually a truly OG in this field. So actually lots of the latest developments in this field can be traced back to his earlier foundational work in this field. So without further ado, let's welcome Amin. Let's give a round of applause. Thanks.
Yeah, thank you very much. So I just recently, so the reason I had some difficulties joining the Zoom meeting was because I just recently moved to Dortmund. And as you may be able to see, I already adapted to my new environment. And so my email address changed. It's now fixed. So yeah, thanks to the organizers for helping me quickly with that problem. What I'm going to speak about is random combinatorial matrices. And at first glance, that doesn't seem to have a lot to do with random inference problems. But at second glance, it does. So let me just briefly recap what kind of inference problems are and why we are interested in them. So over the recent years, over the past decade or so, there has been a great deal of interest in things like the stochastic block model or implanted constraint satisfaction problems, where you are faced with a base optimal inference problem. So your goal is to recover a hidden ground truth by means of indirect observations, and you're in a base optimal setting in the sense that you know the correct distribution from which the examples that are presented to you, for example, the edges in the stochastic block model, are actually drawn. And so perhaps surprisingly, I mean, first, many years ago, this seemed like a purely academic game to play, but perhaps surprisingly over the years, this has had many interesting and important practical applications, perhaps the most prominent of which is new algorithms for things like compressed sensing and similar practical problems by way of probabilistic constructions. And so a general framework for expressing these problems is something called the teacher-student model, where a teacher generates a ground truth sigma star, for example, just a 0,1 vector of size n. And instead of handing this vector directly to the student, is going to also, given sigma star, create some examples that might, for example, be the edges of a graph G. And now the student is presented the examples G drawn according to the ground truth. And the goal of the student is to recover the ground truth as best as possible given these examples. So that means that the student aims to draw a sample from the posterior distribution of sigma star given the observed data. Now, so one phenomenon about, or one key feature of these base optimal inference problems is that generally they are replica symmetric. So this means that if you, so this means the following: if you ask yourself how well is it going to be possible to recover the ground truth, so to what extent can we actually approximate sigma star, then it turns out that this quantity, the overlap between the posterior distribution and the ground truth, actually concentrates on a single value. So to explain this a bit more, maybe let's say that the overlap of two 0,1 vectors of length n is simply just the fraction of coordinates on which they agree. And then what happens is that the overlap between a sample from the posterior distribution and the actual ground truth is going to concentrate on one single value once you condition on G and sigma star, once you condition on the observed data and on sigma star. So of course, a priori, you might think that there's no reason to assume that you have this sort of concentration. A priori, it could be for example, that there are several clusters in this posterior distribution that give you vastly different overlap values, perhaps. But that turns out to be not the case. Instead, what happens is that you get this concentration on one single value. So you don't get more complicated overlap distributions like you might get in a one-step replica symmetry breaking scenario, like, for example, that exists, for example, in problems like in random constraint satisfaction problems, like, for example, random KSAT, or something even more complicated like full replica symmetry breaking that is present in, for example, the SK spin glass model. And so this property that you get concentration on a single, that you get overlap concentration on a single value given the disorder G and sigma star, enables a host of proof techniques. For example, the Eisenman-Sim star scheme, a coupling argument, or simplified versions of the interpolation method. And as a result, it is possible in many of these base optimal inference problems to actually, for example, compute the mutual information between the ground truth and G. So we know a whole lot about these problems thanks to this overlap concentration, which is named replica symmetry, of course, in physics jargon. Now, in a lot of cases, actually in practically all cases that have been studied with any measure of success, an even stronger concentration property holds. Namely, what happens in virtually all known examples of such base optimal inference problems is that your overlap concentrates on one single number, on one single value that doesn't even depend on the disorder. So on the previous slide, we had this conditional expectation here. So the actual random variable, the overlap between the sample from the posterior and the ground truth, concentrated on this conditional expectation, where we condition on sigma star and on the observed data. But actually, in most examples that we know of, or actually in practically all examples that we know of, you can drop this conditioning here altogether. And what happens is that the overlap concentrates simply just on one deterministic value, regardless the disorder. And so this stronger property, the strong replica symmetry property, of course, enables even more powerful proof techniques, such as the stochastic interpolation method pioneered by Barbier and Matrices. And Barbier and Panchenko actually showed that there's a perturbation that you can apply to many inference problems that will precipitate this strong replica symmetry property. And in fact, I don't know of any positive example of a natural inference problem where it was previously known that strong replica symmetry is not satisfied. Now, what I'm going to do in the rest of the talk is I'm going to look at a very particular family of inference problems, namely at inference problems that are actually easy in a computational sense. So one interesting feature of these base optimal random inference problems is that in many cases there's a gap between what you can do information theoretically and what you can do, or what you seem to be able to do algorithmically. And this is one theme where, for example, David Germanik and co-authors have contributed a lot to our understanding. And I trust he's going to talk about this as well at the conference. So in these cases, it makes a difference how much computational power you have at your disposal. This has an impact on how well you can actually recover the ground truth. Now, in the family of problems that I'm going to speak about, that is not the case, but it's not the case for a very peculiar reason. It's not the case because the problems that I'm speaking about are linear. So I'm going to speak about problems from linear algebra, specifically random linear systems, where Gaussian elimination puts you in a position to efficiently sample from the posterior distribution. Nonetheless, even though these problems are computationally easy in any phase of for any values of the parameters, it turns out they are nonetheless rather instructive, and the fact that they have these algebraic properties actually puts us in a position to understand them extremely well, perhaps a lot better than what we can currently do for examples like the stochastic block model. So the random matrix model that I'm going to look at is kind of inspired by low-density parity check codes. In fact, low-density parity check codes are based on precisely such random matrices. We are going to look at a random matrix model where you can effectively prescribe the number of non-zero matrix entries in each row and each column. The matrix is going to be sparse, so a typical row is going to contain a bounded number of non-zero entries, and the same for a typical column. And this random variable D is going to be the number of non-zero entries in a column, and K is going to be the number of non-zero entries in a row. We are going to assume that these random variables are half-way reasonable, so the second moment, and actually a tad more than the second moment, has to be finite. And then we are going to choose the aspect ratio of the matrix so that typically the degree sum in the rows and in the columns match. Specifically, we are going to take a m by n matrix where m is expectation of d times n on expectation of k. And we are going to condition on the event that the total column degree matches the total row degree. Given that event, which is not very unlikely, we can then generate a random bipartite graph with the given degrees. And the linear inference problem that I'm going to be interested in then stems from the bi-adjacency matrix of this random bipartite graph. So effectively, what we are looking at is a random matrix over the field F2 with a given number of non-zero entries in the rows and in the columns, and this matrix is sparse, so the average number of non-zero entries per row and column is going to be bounded. Now, how do I turn this random matrix into an inference problem? What we are going to do is we are going to multiply the matrix on the right by a uniformly random vector sigma star in F2 to the n. So we simply just let our ground truth be a random bit string of length n, and then multiply the matrix A by sigma star. The result is some random vector y in the column space of A. And of course, it's very easy to characterize the posterior distribution of sigma star given the disorder, given A and Y. Namely, the posterior distribution is nothing but the uniform distribution on the set of linear, or on the set of solutions to the linear system A sigma equals Y. So in particular, it's also easy to get at the entropy of the posterior, at least algorithmically, it would be easy. We just run Gaussian elimination and calculate the dimension of the kernel of the matrix, or in linear algebra jargon, the nullity of the matrix. And so all of these things are computationally easy, and maybe given that they are easy, and given that linear algebra is full of beautiful symmetry properties, we might be able to study this model very closely. So for example, one symmetry property that is peculiar to such linear problems, and that is, for example, absent in things like the stochastic block model, is that I can guarantee you that for a sample from the posterior, it's either going to be the case that if you look at one single coordinate, sigma I, you look at one single coordinate in a sample from the posterior, for example, at the 101st coordinate, then what's going to happen is that this single bit is either going to be uniformly distributed over the value 0 or 1, or it's going to be deterministically frozen to one particular value. And so this doesn't necessarily mean yet that your random matrix model is replica symmetric or strongly replica symmetric, because it could still be that coordinate 101 and 207 are correlated in some very complicated way. But at least it shows that the marginals of the posterior distribution cannot be very complicated objects, and that is in contrast to many other inference problems. And so in particular, we are going to be interested in the set f of a of frozen coordinates that always deterministically take the same value. So just to give you one example of a specific random matrix that you might know about already, of course, is one specific example is the random 3-Xorsaat problem, where you fix k, the number of non-zero entries in the rows, to be 3, and where the distribution of the number of non-zero degrees in the columns is a Poisson D distribution. And so this boils down, or this is just identical to saying that you drop down dn on k independent k array or independent 3-array equations. Right. So, and interestingly, or maybe, yeah. So interestingly, it turns out that there's a fairly simple way of computing the entropy of the posterior distribution, or in other words, the nullity of the matrix, or at least the approximate or the asymptotic nullity of the matrix. Namely, the nullity or the asymptotic value of the nullity comes out in terms of a strongly simplified version of the beta free entropy that we know from the cavity method. So specifically, normally when you speak about the beta free entropy, it involves a variational problem where you are asked to optimize over a space, an infinite dimensional space of probability measures. Now, in this case, in the case of linear problems, because of this peculiar property of the marginals, it turns out that you don't need a space of probability measures to take into account, but instead what you can do is you can just reduce it to a one-dimensional optimization problem on the real numbers, on this functional phi of z, which comes in terms of the generating functions of the 2 degree distributions. And so then your nullity is going to converge to, or your free entropy is going to converge to this particular, to the maximum value of this particular functional. And so, yeah, returning to the example of random 3-Xorsaat, you can then use this functional, for example, to find, to easily find the random 3-Xorsaat threshold. Namely, if you plot this function phi of z for increasing values of d, starting at d equals 0 and then moving your way up to d equals 3, what you see is this little cartoon here. So the bluer curves are for smaller values of d. The more red you see, the larger the value of d. And initially, for small values of d, the max of this function is attained at 0. And so long as the max is in fact attained at 0, you are in the satisfiable regime of the 3-Xorsaat problem. But then eventually what happens is that a second max near 1 somewhere pops up. And as you make d bigger and bigger, the second max near 1 is going to take over as the global maximizer. And the moment that happens, you crossed the 3-Xorsaat satisfiability threshold. And the 3-Xorsaat satisfiability threshold is also the point where you start to see frozen coordinates in this problem, where suddenly, in other words, you can get a good non-trivial approximation to the ground truth from in this linear inference problem. So the moment you can do non-trivial inference is precisely the satisfiability threshold in random 3-Xorsaat. And of course, this has been known for a long time. For example, the 3-Xorsaat threshold was first computed by Dubois and Mandler using a second moment method, a different technique than what is behind the proof of this theorem that I presented. But none of this is new, let's say. It's just kind of recapping the 3-Xorsaat threshold in terms of these random inference problems or linear inference problems. And also, it is very easy to see that in this Freak-Saucer problem, you get strong replica symmetry, except perhaps, but for all I know, this is not proven, right at the satisfiability threshold. So another natural random matrix model to look at, and this turns out to be rather instructive, is the Bernoulli random matrix model. In this random matrix model, you don't fix the number of non-zero entries in the rows. Instead, I mean, this is kind of, let's say, the easiest random matrix model you could think of, presumably. Instead, what you do is you simply just say every entry of this, of an n by n matrix, of a square matrix, equals 1 with probability d on n independently. And in other words, this means that in my random matrix model, the degrees of the rows and the columns, then the number of non-zero entries in the rows and the columns, both have a Poisson distribution with the same mean d. And now if you plot the phi function for this particular random matrix model, for this choice of degree distributions, what you see is this cartoon here, namely initially for very small values of d, for d at most e, what happens is that your function is concave. There's a unique maximizer, yeah, somewhere around here maybe. And at d equals e, you see that you get a critical phenomenon. So the first derivative vanishes and the second derivative as well. But then for d greater than e, what happens is that two maximizers appear at two distinct points, one a little bit to the left, one a little bit to the right of the former maximizer. And then there's a third local min in the middle. And interestingly, these two global maximizers are exactly identical. So in Saucer, we saw that one maximizer eventually always takes over, either 0 or the one close to 1. In this case, that's not true. In this example, that's not true. Instead, you get two maximizers where the functional takes exactly the same value. And that might already be a hint that maybe some sort of a critical phenomenon is going on. I'm going to write alpha lower star for the lower maximum here, for the maximum on the left, alpha 0 for the local min, and alpha upper star for the maximum on the right. And interestingly, because of this critical phenomenon, this linear inference problem on the Bernoulli random matrix is actually an example where you don't have strong replica symmetry in general. So it's an example where the inference problem is replica symmetric, but not strongly so. To be more precise, for small values of d, in this regime where you only have a single maximizer, this linear inference problem, getting at sigma star given the matrix and the right-hand side vector y, is strongly replica symmetric. And in fact, we can calculate the overlap, and the overlap is precisely, well, it's an affine shift of the maximizer, the unique maximizer of this phi functional. But in the case where d is greater than e, it turns out that you still have replica symmetry. So once you condition on the matrix A, the overlap is still going to concentrate on a deterministic value, but you don't have strong replica symmetry anymore, in the sense that the magical value on which your overlap concentrates actually vacillates between two different distinct numbers, 1 plus alpha lower star on 2 and 1 plus alpha upper star on 2, and is approximately equal to either of these two values with probability about a half. So essentially your matrix or your model performs a coin flip, and with probability half you have the lower overlap value, or the probability half with the remaining probability you have, you see the higher overlap value. So yeah, that's interesting, and it's kind of the let's say the first natural example of such a phenomenon where you have replica symmetry but not strong replica symmetry that I know of. And what makes it kind of, and so of course, if you think about such a critical phenomenon, it's maybe not a surprise that this is difficult to prove. I mean, I wouldn't be surprised if it turns out to be correct that in many other problems, for example, at phase transition points, you also get this critical phenomenon for the overlap, that it vacillates between two values or maybe between several values. But in this example, we actually have it in an entire phase of the problem for all d greater than e. And we can, in fact, prove it. So here's the proof strategy, or an outline of the proof strategy. The first step of the proof is that we establish replica symmetry via the pinning technique that was used in prior work. And first introduced, as far as I know, by Andrea Montanari in work on low-density parity check codes. Then what we are going to do is we are going to study the number of frozen variables, and we are going to argue that the number of frozen variables either concentrates on alpha lower star times n or on alpha upper star times n. So either the fraction of frozen variables is given by the left maximizer of our functional, or it's given by the right maximizer. And finally, what we are going to do, and that's sort of so this is sort of the hammer part of the argument as I see it. So we first show that you must be close to either of these two values, and then the end part is that we do an explicit combinatorial construction by way of the warning propagation message passing algorithm. To show that, to find an explanation, a combinatorial explanation of how these two values for the number of frozen variables can come about. And so specifically, we are going to construct a critical set S of variables that freeze with probability about a half. So we are going to be able to put our finger on some specific variables and say, well, these variables are kind of on the verge of freezing. And either, they are on a tipping point, and either they tip to the freezing side or to the unfrozen side, and each of these happens with probability half, and that's going to determine whether you see the lower value or the upper value for the number of frozen variables. So let's begin with the replica symmetry part. By replica symmetry, I mean that if you look at a bunch of random coordinates in your posterior distribution, so you pick any finite number L of coordinates randomly from the n coordinates, and you look at the joint distribution of the posterior, or the joint value of the posterior on these finite number of chosen coordinates, then what you see is typically a product measure. So for almost all choices of any finite number of coordinates, the values that you observe at these L coordinates are going to decouple. They are going to be essentially, or in fact in this case, exactly stochastically independent for almost all choices of the coordinate values. Of course, this property cannot possibly hold for all choices of L tuples of coordinates because of local correlations. But what this is saying is that there's no extensive long-range correlations between the values of these variables. And the proof of this is fairly easy. It actually follows from Andreas' variant of the pinning lemma, or what I call the pinning lemma. And so in this specific model, the observation is that the model is self-pinning. So in the pinning lemma, what happens, what you do is you take a finite number of random coordinates and you share with me the value of these coordinates via a side channel. And once I have this extra information, for me, from my viewpoint, it turns out, and this is the result of some information theoretic calculations, that the problem becomes replica symmetric. Now, in this case, in this particular random matrix model, we don't actually need the side channel. We don't need to do anything in particular to modify the model. And so instead, what we can do is we can use unary equations that are present in the random matrix model anyway. So these unary equations that come from rows of the matrix that happen to just contain one single non-zero entry effectively perform this function of the side channel. And because of very high probability, we have plenty of these unary equations in our model, we don't have to modify the matrix in any way. So as an application of the pinning technique, we can directly say that the model is going to be replica symmetric. No need to do, or no need to take any action. Now, given that we know this replica symmetry property, we can now study the number of frozen variables. And so this is going to use a coupling argument. Similar arguments have been used in the past for the study of random inference problems, but in this case, it turns out to be particularly elegant and, you might say, straightforward. Namely, what we are going to, our goal is to study the number or the fraction of frozen variables in our linear system. So how many coordinates are actually deterministically fixed to one particular value. And we are going to do that indirectly by way of a fixed point equation. So we are going to show that the fraction of frozen variables satisfies a fixed point equation. And the way we do this is by observing that our random matrix model is invariant. I mean, the random matrix model itself is invariant under a small local perturbation. Namely, what I can do to my random matrix model is I can simply just add one extra n plus first variable along with a bunch of adjacent checks, a bunch of linear equations where this where this new variable appears. So this is a Poisson D number of new extra equations. And then I'm going to connect each of these new extra equations with the bulk of my coordinates, with the other n coordinates, by including in each of them Poisson D of the remaining or of the first n coordinates of my linear system. And so roughly speaking, from the viewpoint of an outside observer, this perturbation is impossible to notice. So the total variation distance between this modified model, roughly speaking, and the original random matrix model tends to 0. And so whatever property the original random matrix model has is also going to be valid for this new modified model. And in particular, if alpha is the random variable that counts the number of frozen, or the probability that a random variable in my linear system is frozen, then alpha is going to have to satisfy a fixed point property. Namely, this variable here would be frozen if and only if, for one of these equations, all of the adjacent variables are frozen. And we can express that probability in terms of the number of frozen variables of the bulk matrix that happens on the previous n coordinates. And so we can derive a fixed point equation for the fraction of frozen variables. And it turns out that the fixed points of this equation are precisely the 3 stationary points of our beta functional, kind of like what you see in the leaf propagation, where the fixed points are in one-to-one correspondence with the stationary points of the beta free entropy. So that's a step forward, but it leaves us with a new problem. Namely, we have to somehow rule out the unstable fixed point. And so this is a new argument that I haven't actually seen before in the context of random inference problems. And so here what we do is we perform a moment calculation. So we study carefully some combinatorial properties that would necessarily be present if actually the unstable value alpha 0 would occur as the number of frozen variables. And in that case, we can show that essentially the freezing of these coordinates must be caused by a warning propagation fixed point. So we can construct some message, combinatorially construct some messages, some warning propagation messages that would have to satisfy fixed point equations for in this scenario. And then we calculate the expected number of such warning propagation fixed points. Turns out there's not all that many of them, or to be more precise, there's not enough of them to make this occurrence that alpha 0 is the middle, sort of this minimum is the correct answer, a likely event. And therefore we can conclude that only the two stable fixed points, or the two stable, or the two local maxima of the beta functional are conceivable values for the fraction of frozen variables. So that's fine. Now what we are left to do is we are left to argue that both of these values, alpha lower star and alpha upper star, come up with equal probability for the fraction of frozen variables. And to that end, what we do is we now perform a combinatorial construction, sort of an enhanced version, or a significantly enhanced version actually, of the construction of the usual two-core of a hypergraph. And so specifically we construct, or we put forward an enhanced version of warning propagation, where instead of the two values frozen and unfrozen, you now have a third value, slush, which basically means combinatorially that these variables are on the verge of freezing. And using this enhanced version of warning propagation, we can then explicitly put our finger on these slush variables that are just about critical. And using a symmetry property that is inherent in the model, it is then possible to argue that these slush coordinates freeze with probability about a half. To be more precise, if I look at the minor of the matrix induced on this slush part that is just on the verge of freezing, then the slush is going to be nearly a square matrix. And whether or not it has more rows than columns, or the other way around, determines whether the slush is going to freeze. And so that's going to then determine whether the overall number of frozen variables takes this lower value or this upper value. So yeah, to wrap up, what we looked at is what I think an instructive example of an inference problem. Although it's computationally easy, I think it's still an interesting combinatorial phenomenon that we are seeing here. Namely, you have this Bernoulli random matrix that has one single parameter d, the density of non-zero entries. And for almost the entire regime of d, this model turns out to be critical, in the sense that it is replica symmetric like any base optimal inference problem, but it is not strongly replica symmetric in the sense that the actual overlap value is just simply vacillates between two different possible values, alpha lower star and alpha upper star, that it can take. And so the proof is based on this combination of kind of an inside-out argument, this fixed point argument where we use implicit properties of the random matrix, and then an explicit combinatorial construction. So yes, I thank you for your attention. I'm sorry that I can't be there with you, but our teaching term just started this week, and I wish you a great workshop.
Okay, so I think we have enough time for questions.
Okay, hi Amin. So just one small question I didn't get from the theorem. I didn't remember whether you can compute what is the probability of each of the two events.
Right. So, yeah, each of these comes up with probability half.
And can you tweak the model to have other probabilities, or is
that's a good question? We haven't. That's a great question. We haven't looked at it. but that's definitely something to look at. So,
but it's not forbidden by some simple symmetry, I guess.
So in this model, actually, there is an inherent symmetry, namely that the matrix, the distribution of the matrix is invariant under transposition.
Yeah.
But
if you move a little bit away from the square matrix.
Right. So if you move away from the square matrix, what happens, I mean, in this particular model, what happens is that you, so if you do the same thing, if you look at this Bernoulli matrix and you move away from the square case, what happens is that you recover strong replica symmetry. So you might say the phenomenon is still kind of lives on a critical line in this model.
But you could think that the aspect ratio is 1 plus order of 1 over square root of n, right? And then
yes. Exactly. So so conceivably there could be some middle ground where you can actually get something interesting. When I first saw this, I was assuming that somehow the probability that one of these values comes up might be related to the second derivative of this functional here. But that turned out to be not to be the case. So I think it would be interesting to see if you find other examples where, yeah, your beta free entropy has several maximizers with the same value, and maybe you get some, yeah, non-trivial probabilities out. So yeah, I think that's a great question.
Okay, any other questions?
Can I ask a question?
Yeah, go ahead.
Okay. I mean, if I understand correctly, is as d goes to infinity, alpha star approaches 0, alpha lower star approaches 0, alpha larger star, upper star approaches 1.
Yes.
So is the implication of that is that if you solve the inference problem, which you can do efficiently, that you, with like half probability, you recover the full signal if you're lucky, and with probability half, you have almost no chance of learning anything about the model, or what's the interpretation?
So. Yeah,
okay.
Precisely so. I mean, that is what would happen if you were to push d to infinity. Yeah, exactly.
So this is like half all or nothing phenomena.
Yeah, you could say that, yes.
Interesting. Thanks.
Okay, any other questions? From the Zoom? Chris, do you have a question? Okay, so if no question, then let's thank the speaker, Amin, again. Yeah, so we're going to come back about, I think it's 30 minutes from now. It's at 10:15, if I didn't make a mistake. Okay, see you in a minute.
So I got the although with local, I think it's impossible to do this. So if the matrix is full, right?
Actually, like a more chill drive.
No, 80, yeah, no, I've done that drive in the winter for sure to go to.